Hello teachers, so we're moving on to a new topic, transformations, and in section 14-1 we're going to talk about translations, rotations, and tessellations. So when you finish this section, you should be able to understand and explain transformation of the plane, isometries and their properties, translations and rotations, coordinate representation of translations, rotational symmetries, tessellations or regular shapes, and creating tessellations with isometries. So we'll start out with definitions. Any rigid motion that preserves length or distance is an isometry. A translation is just a type of isometry. Any function from a plane to itself that is a one-to-one correspondence is a transformation of the plane. And because transformations are functions, they have properties of functions. And we'll list some properties of transformations. A translation is a motion of a plane that moves every point of the plane a specified distance in a specified direction along a straight line. A figure and its image are congruent, and the image of a line is a line parallel to it. So notice what's happening. This is a great image of a child on a slide, and that's exactly what's happening here. So notice the notation. We have something called a slide line, and you see the slide line is along here, so this is the direction the image is moving. The original is also called the pre-image, okay, and this is the image, the new image that's a copy. Notice these are congruent, so we're not changing the size of the image whatsoever, okay, and then you have a slide arrow or a vector, and this tells you the distance that the slide in or the translation has moved in. To construct the image of an object under a translation, we first need to know how to construct the image A primed of a single point A. So when you do these, always focus on a single point to start with, and then just move each point one at a time. So for this particular translation, I'm going to highlight what we're actually doing here. So you see that we have a line segment AB. So I'm going to highlight that. And the goal is to create a copy of that line segment. We're calling that an image. Now notice at the bottom, it says slide arrow or vector. So we're supposed to move AB this distance over. Notice they labeled it D, okay, and in that direction. So notice the slide arrow vector gives you a distance and a direction. And so the copy ends up right over here. It says to construct the translation image A primed of a point A with a compass and a straight edge, if that's all you had, construct a parallelogram MA primed N. So notice that's not what's in this picture, but you have MA, right, and then A primed N. And so if you already have your slide vector, and you would construct the parallelogram by creating a straight line from A to M, okay, and then make sure you do a parallel line here and then connect the dots here, and that would give you your A primed. And you need to do the same thing to get your B primed value and connect the dots, and there would be your image, okay. Now for our first official example, we're instructed to find the image of AB, so you see the line segment here, AB, under the translation from X to X primed pictured on dot paper. Okay, so we're supposed to do to AB what happened right here from X to X prime. Now let's talk about this. So it looks like, it's at an angle here. The best way to talk about that is a vertical and a horizontal component. So notice, first of all, we're moving down 2. So that's a good way to think about that, is we're moving the point down 2, but also we're moving right 2. So we could do that. We could look at A, and we can move A down 2. Notice I did that, so down, don't count where you are, down 2, and then right 2. So this would be A primed, and let's do the same thing for B. So count B down 2, and then right 2. I lost track. Down 2, right 2. That would be here. And then that is a B primed, and then you connect the dots, and there's your image. And here is the textbook's explanation, which is great. The image of each point on the dot paper can be obtained by first shifting it 2 units down. So again, so here was the original, okay, or the pre-image. And this is our vector. So we moved 2 units down and then 2 units to the right. So we did that with both points. Again, A, we moved 2 units down, 2 units to the right, and that gave us A primed. And then B, we moved 2 units down and 2 units to the right, and that's B primed. And you see your image is copied A primed to B primed in blue. Easy enough, right? Now, often you're given coordinate representations of translations, and for me personally, that's the easiest way to handle it. So notice what we have going over here. Here's the coordinate representation. So it's saying that when you take an x value and you plug it in, you add 5 to it. So notice that's what we do. We take -2 and we add 5 to it, and that's going to give us 3. And the y value, we subtract 2. So we take 6 and subtract 2 from it, and that gives us 4. And you do that for all your points. Now, where did they get these points from? You might have to just look at your system here and plot those points. So they told you what they were, but let's just check it out. So I'm looking at the point A on the green triangle, and this is the origin, 0, 0 right here. So if I count left 2, that would be -2, and then 1, 2, 3, 4, 5, 6, and so that's where the -2, 6 came from. Okay, and then we plug it in, again, that's going to turn into the 0.34. So notice, again, we moved right 5, and then down 2, or we just plot the 0.34. So 1, 2, 3, and then 1, 2, 3, 4. There it is, our 0.34. So we do it again. We look at the point B. Notice that's labeled 0, 8. We could do that on our own if we had to. So that is 0, 1, 2, 3, 4, 5, 6, 7, 8. That's definitely 0, 8 up there. And then we plug it into our coordinate representation of the translation. So 0 plugs into the x value. 0 plus 5 is 5. 8 plugs into the y value. 8 minus 2 is 6. And we plot the 0.56. And you'll see that is right there at B. Or you could say it moved right 5 and down 2. And finally, our C value, you notice it is at 2, 3. And that's how it was labeled here. C is 2, 3. I plug 2 into my x value. 2 plus 5 is 7. I plug 3 into my y value. 3 minus 2 is 1. And then we plot the C primed, which they didn't put the little primes over here on our pink triangle, but that's what it is. Those are all the prime values, and that is at 7, 1. And then there is our pre-image in green and our new image in pink. So if you use coordinate systems to represent a translation, notice that translation is a function from the plane to the plane such that every point x, y corresponds to the point x plus a, y plus b. Now keep in mind, a doesn't have to be a positive number, like we had some negatives just a minute ago. When we did our problem, we had x plus 5, y minus 2, so b was actually negative. Where a and b are real numbers, could be any real numbers, this can be written symbolically. So notice the notation here. You say xy moves to x plus a, y plus b. In other words, when you have coordinates, you just plug them in. X value goes here, y value goes here, and that creates new x, y values to represent your translation. So here's example 2. Find the coordinates of the image of the vertices of quadrilateral A, B, C, D under the translations in parts A through C. Of course, I have just part A right here. So let's find our coordinates. So notice we have 4 vertices of our quadrilateral. Let's look at them one at a time. So we can say 0, 0 turns into, Well, I plug 0 as my x value, so I plug it in for this x. 0 minus 2 is negative 2. 0 plugged into the y value here. I add 4 to it. That gives me 4. So 0, 0 turns into negative 2, 4. Then I'm going to use my, let's do them in alphabetical order. My B point is 2, 2. Notice it's labeled for me already, but it's not always labeled for you. You might have to do that yourself. All right, and again, I'm going to plug my 2 in for my x. 2 minus 2 is 0. I'm going to plug in 2 for the y here. 2 plus 4 is 6. And my new image point is going to be 0, 6. That would be my B prime. Let's plug in C. C is labeled 4, 0. And 4 minus 2 is 2. 0 plus 4 is 4. And finally, D is labeled 2, negative 2. And I plug 2 in. 2 minus 2 is 0. And negative 2 plus 4 is 2. All right, now I have this typed up. Should be the same exact points. And notice that it is. I didn't label my points as A primed, B prime, C prime, D prime, but I think you're aware of that. Okay. Now part B, a translation determined by the slide arrow from A00 to A primed, which is negative 2, 4. Okay, now this is supposed to be a completely different problem. This is just a different way of depicting a translation. So it's saying that 0, 0, let's write that down. So 0, 0 is going to change to A primed, which is negative 2, 4. Now, if we were to think about that in coordinate form, well, let's just try to do that. So 0 turned into negative 2. So that means we're taking our x and subtracting 2. What happened to the y value? Well, we took 0 and it turned into a 4. So we're taking our y and adding 4. Now, if you think about it, if you want to go back and look, that's exactly the translation we had in part A as well. So it turns out this is just a different way of depicting exactly the same translation. So this is the same translation as A, and there we go. This is the same translation as in part A. Now let's look at part C. Different question. So a translation determined by the slide arrow from S4, negative 3 to S primed 2, 1. So they gave us a slide arrow that's at 4, negative 3. I really want to put it just on my graph here. 1, 2, 3, 4, negative 3. That's way down here. Okay, to 2, 1. So 2, 1. Yeah, I have that in the right spot. So that's our slide arrow. Okay, now you could think about it like this. So again, if we're going from S4, 3 to S primed 2, 1, again, let's try to write it in coordinate form. So 4 changed to 2. So we took our x value and subtracted 2, right? That's what you would have to do to plug in a 4 and get an answer of 2. What about the y value? Okay, so we took a 3 and it gave us a 1. So that would be y minus 2. All right, I knew this wasn't how this was supposed to come out. I have a typo. So notice it was negative 3. Negative 3 to 1 is not subtracting 2. Negative 3 to get up to 1 is actually adding 4. Now, I wouldn't have caught that at all, except I knew that this answer was going to be the same translation as A as well. Remember, that was our original A translation, x minus 2, y plus 4. So once again, here we go. The translation from S4, negative 3 to S prime 2, 1 moves an x coordinate negative 2 units and a y coordinate 4 units. And thus every point xy moves to a point with x coordinates x minus 2, y plus 4. This is the same translation as in part A. Just 3 different ways to depict a translation. And this is actually a picture of that translation. So remember, they gave us the points 0, 0, 2, 2 for B, 4, 0 for C, and 2, negative 2 for D. And when you run those through, x minus 2. Notice every x value moved over 2. A moved over 2 and then moved up 4. B moved over 2 and then up 4. C moved left 2 and then up 4. And then D moved left 2 and up 4. And that gives us our translation. Now again, you could just plot those 4 points, connect the dots. It's going to be exactly the same shape. They're congruent. They're just in a different position. Now, translations are not the only thing we can do. We can also perform rotations. So a rotation is a transformation of the plane determined by holding one point, the center. So we're going to, for a rotation, we're going to hold one point, the center, fixed, and rotating the plane about this point by a certain amount in a certain direction. A certain number of degrees, either clockwise or counterclockwise. So here's a depiction of how you would do this. To me, these are slightly more complicated to visualize than a translation where you just go left, right, up, and down. So what you have here is your original on the left, okay? And you could copy it with tracing paper. This is one way to do it. And you would also need to copy your center. Remember, that thing is called the center. We're going to turn around the point O. And then what you do is you take your point C. Notice they have a straight edge connecting that part. And then you're supposed to turn at a particular angle. So you will be given an angle. Say, for instance, 60 degrees. You would measure that angle or construct that angle and then move your C primed over that many given degrees. That would be your C primed. And then you would reconstruct your figure. So all the points would move over that same rotation. Again, point O is called the center because you're rotating it about that point a certain number of degrees. Also, when you do these, be really careful. They will either say clockwise or counterclockwise rotation. I found myself doing some of them wrong because I was just going counterclockwise when it was supposed to be clockwise. Now, something you might have thought about is special rotations. A rotation of 360 degrees about a point moves any point and hence any figure onto itself. Such a transformation is an identity transformation. Any point may be the center of such a rotation. A rotation of 180 degrees about a point is a half turn. So anytime you see half turn, that's a rotation of 180 degrees. And again, if we rotate 360 degrees, that's an identity of transformation. That's exactly where you started. Now let's talk about tessellations of the plane. Tessellations of a plane is the filling of the plane with repetitions of figures in such a way that no figures overlap, and there are no gaps. So notice what this is. It's called Study of Regular Division of the Plane with Reptiles, and that's by M.C. Escher, who is a great, fantastic artist that works with tessellations and other mathematical type images. But notice that it's the same figure just repeating. It looks like it rotates, and there are no gaps at all. If you think about just tiles on the floor, that's a more basic tessellation, but that is a tessellation. Let's look at regular tessellations. So tessellations with regular polygons are both appealing and interesting because of their simplicity. So you can have tessellations with squares. Plenty of you have seen square tiles on the floor. You could also, this almost looks like a brick design, and then you could have tessellations with equilateral triangles. Notice how they all fit together nicely, and it works with hexagons as well. I know you've seen tilings with hexagons before. Well, you can create your own, turns out, and it's a really neat thing to do. Consider any polygon known to tessellate a plane. So again, you can consider any of these for now because we know that they tessellate planes. We'll talk more about what works and what doesn't in just a minute, but just picture any of these shapes. All right. On the left side of the figure, you could draw any shape in the interior of the rectangle. So notice we drew this zigzaggy shape over here on the left side. Cut this shape from the rectangle and slide it to the right by the slide that takes A to B. Okay. So we just picked up that cutout piece and then put it on the other side. All right. the resulting shape will tessellate the plane. So this will fill the plane, this piece over and over and over again. So you notice when you do another one, this piece will fit right on top of this piece, just like puzzle pieces. That's not the only way you can do it too. A second method of forming a tessellation involves a series of rotations of parts of a figure. And if I go back to the lizard image here, this was created that way. As a matter of fact, if you look hard, you can notice the hexagons, okay? And it was done very similar to what we're about to do here. So a second method of forming a tessellation involves a series of rotations of parts of a figure. So start with an equilateral triangle. Again, the lizards started with a hexagon, okay? Choose the midpoint O of one side of the triangle and cut out a shape. So notice the O is the midpoint of a side, and just cut out the shape over here. It says being careful not to cut away more than half of angle B. So do not cut into more than half of angle B over here. And then rotate the shape clockwise around point O. So notice this is a rotation. Okay, it's a 180-degree rotation, right? And you just rotate it right over here, and now it's pointing outward. Okay, and this will also fill the plane. As a matter of fact, they have that there. Neat, huh? Now, which regular polygons can tessellate the plane? You know, I warned you that was coming. Will just any polygon, a regular polygon, fill the plane? Picture different polygons in your head and think about how they might connect up. Will they leave gaps, or will they all fit together nicely? It says to understand this, look at the tessellation using hexagons. So this always makes me think of a bathroom floor, because I grew up with a bathroom floor that looked a lot like this. But notice at the vertex where these tiles meet. Okay, a hexagon has an interior angle of 120 degrees. So this one's 120 plus this one's 120, that makes 240, plus this one's 120, that makes 360 degrees. It fills the plane. Well, what if you were dealing with polygons that don't add to be 360 degrees? As you can imagine, that might be a problem. It says around a vertex of any regular tessellation, we must have an angle sum of 360 degrees. So this is important. Okay, so 3 times 120, which is what's happening for our particular tessellation, is 360. The interior angles of a hexagon measure, and you remember how to calculate this? This is how you calculate interior angles. Remember, it's the number of sides, which is 6 for a hexagon, n minus 2, times 180, and then divided by n. That's the formula for finding interior angles of a regular polygon. Okay, so again, 120 degrees. If we fit 3 of them together, that fills the plane. Well, this time let's think about pentagons. Okay, remember pentagons have 5 sides. I could calculate that angle, right? It would be, formula would be 5 minus 2 times 180 degrees divided by the number of sides, which would be 3 times 180 divided by 5, which is actually 108 degrees. So each angle is 108 degrees. So if you start putting them together and you fit them together, you have 108 plus 108 plus 108, and that adds to be what, 324 degrees. So that's not 360. Could we squeeze another one in there? Well, no, because if you squeeze another one, you would be over 400 degrees. And that would be too much. There would be overlap. As a matter of fact, I've got a depicting that, right? So a pentagon, a regular pentagon, does not fill the plane. So let's talk about what will fill the plane. Let's see if we can figure out all the regular shapes that would fill the plane. So here's an example. Number of sides, we have a triangle. Each of those are 60 degrees. What's your thought there? Would that work out? Okay, then you have a square, which is 90 degrees. Let's think about this. Would that work out? Hey, we already know a pentagon is off the list, right? Because we tried that, didn't fit together. Either you had a space or if you threw in an extra one, they would overlap. So a pentagon is out. We've already decided a hexagon works. Matter of fact, you've already seen a triangle and a square work, and you've seen a hexagon work out. Well, a heptagon, remember seven-sided figure, the interior angles are 900 divided by 7. That's not even a nice whole degree measure. What do you think? Will that work? What about an octagon or a nonagon or a decagon? Well, I've got another slide for you here. Remember, they have to add to 360 degrees. So don't we need these angles divisible by 360? And so notice the triangle, if you divide that by 360, 6 of them will fit in there, okay? Or 360 divided by 90 is 4. 360 divided by 108 is not a whole number. That's why the pentagon was out. 360 divided by 120, that worked out great, right? It was 3 times. So far a triangle, a square, and a hexagon. Well, look, we didn't get a nice whole number here, so we couldn't use a heptagon to fill the plane either because it didn't go through there enough a whole number of times. Look, 2.6, octagon's out, nonagon's out, decagon's out. It's not going to work out. As a matter of fact, it says since 360 divided by a number greater than 120 is smaller than 3, and the number of sides of a polygon cannot be less than 3, no regular polygon with more than 6 sides can tessellate the plane. Okay, so basically we know them. All the regular polygons that'll work are just a triangle, a square, and a hexagon. Okay, but these are regular polygons. On the other hand, when more than one type of regular polygon is used and an arrangement of the polygons at each vertex is the same, the tessellation can be semi-regular. So notice we have a combination in this case of a hexagon and a triangle. So that's pretty cool. That also fills the plane. Now, what about tessellations with other shapes? Although there are only 3 regular tessellations, a square, an equilateral triangle, and a regular hexagon, many tessellations are not regular. It says one factor that must always be true is that the sum of the measures of the interior angles around a vertex must be 360 degrees. Okay, so that's important. So the sum of the measures of the interior angles around a vertex must be 360 degrees. Check this one out. It's pretty cool. A regular pentagon does not tessellate the plane. However, some non-regular pentagons do. And so notice we have a pentagon. It's got 5 sides, but it's not 5 of all the same angles and all the same side lengths. But that definitely fills the plane. It goes on to say, the following 2 tessellations were discovered by Marjorie Rice. This was in the 70s. And the problem of how many types of pentagons tessellate remains unsolved today. So there are even more images in your textbook that show other pentagons that tessellate the plane and some unusual shapes, but they're all pentagons. And of course there's lots of other figures that will tessellate the plane as well. And not only that, there's an infinite number of tessellations that could possibly exist because of this fun trick and this fun trick, right? You could do these on your own. You could do these with your classes. It makes for some really interesting art. Okay, well, that's the end of my lecture. So I hope that it made good sense to you. If you struggle with the homework or if you have any questions whatsoever, please let me know. Otherwise, I hope you have a great day.